There are obviously, as you've heard from Larry and others, there's a large number of collaborators, scientists to choose from. We also wanted to have diversity from across the country. Certainly one of our leaders in anesthesia research and anesthetic mechanisms is Rod Eckenhoff, professor at the University of Pennsylvania, also a close collaborator with TED, so it's a pleasure to introduce Rod.
Thank you, Mike. It was a real distinct honor to be invited to do this. This is something I just couldn't possibly turn down. So this is going to be a little different. You're going to hear a little bit more science now, or at least the science that Ted participated in later in his career. And I'm not going to apologize for that because this is what my relationship with Ted was built on pretty much entirely. I got to know him better personally later in my career and his career. And also because I think Ted is here. I think Ted's watching us. I think Ted would be intrigued by some of the stuff that I'm going to present to you today because some of it's unpublished. But actually, unfortunately, he can't challenge me anymore. He was really good at that. Okay. So that, like many of us, we got our start with these books. This is one of the few textbooks I actually paid full price for. And these little monographs, isoflurane, desflurane, and so forth, I found extraordinarily useful as I got going in my scientific career. So I thank Ted for those things. So here's where I really got my introduction to Ted Eager. This is not Ted Eager, but this is how I got my introduction. So this was a paper published by Alex Evers back several years ago in Nature. Right? So this made a big splash. And basically what he was saying in this paper, that using NMR, as you inhaled more and more halothane, I think it was, that you would have saturable binding in the brain. And so this was kind of a new thing, the idea that anesthetics interacted with proteins and therefore were specific and saturable. And so this made kind of a splash. The implication was that there were abundant saturable binding sites, presumably protein, in the brain. Well, so this guy read this paper, I'm sure as we all did, and was skeptical. This was one of Ted's principal characteristics. He was a skeptic. And so he said, he's a pharmacokineticist, right? And so he said, this is all pharmacokinetics. This is not pharmacodynamics. This is not binding. And so what he did is he published two papers back to back, the absence of saturable binding, and again, the absence of saturable binding. One was in vivo, one was in vitro. Alex's response to that was correction. So Alex got two papers in Nature. But this what I learned from this interchange, and this was a fascinating interchange. What I learned, so this is, I titled this talk "The Unintentional Mentor" because neither Ted nor I went into our relationship as a mentor-mentee relationship, but I learned a lot. And so what I learned from this was, be careful of Professor Eager. But the second thing I learned was that this issue of specific binding to protein was really still wide open. Just because there wasn't abundant saturable binding didn't mean there wasn't saturable binding in some ways. And so at the time, I was in my T32 postdoc working with a guy named Andrew Somlyo. Andrew was a professor of physiology there, and he was teaching me a technique called electron probe microanalysis. And I adapted that to look at halothane. So here's halothane. It's got this funny looking bromine here. And by using this technique, which basically allowed me to fix the bromine in a tissue section and measure its concentration. And in fact, I can measure its concentration down to a single cristae of a mitochondria. It was very cool. At least I thought it was very cool. And so we published this paper in PNAS because, again, it was kind of a cool tour de force. And I presented this proudly at an ASA meeting in about 1989. And then this guy stood up at the end. Many of you know this guy. And here's what he said. Rod, it'll never be useful. So I was really kind of deflated. Everybody here knows this is a typical comment out of Jim Trudell. And but eventually I found out that he was right. This was not the approach to get at specific binding of anesthetics because you can't get rid of non-specific binding. So I went back, somewhat deflated, to the lab, and I worked with this guy, Henry Schumann. And Henry and I developed, instead of using an electron beam to fix the anesthetic in tissue, we used light. Made a lot more sense because now we could do bigger samples, we could do biochemistry, we could find out, in fact, is it binding to specific proteins. Now notice in that previous paper, I didn't use the word saturable. That was not in there because I knew what had happened to Dr. Evers. And so here, finally, we use the word saturable. And I was expecting a little bit of pushback from the West Coast. Didn't happen, so we were encouraged. Basically, what we're able to show is that there was, in fact, saturable binding if you looked at synaptosomes, but there was a lot of nonspecific binding too. So that's why you couldn't see it with the NMR signal, but you could see it with this approach, which was called photoaffinity labeling. We did some more work. We got a little bolder. We started looking at proteins in particular. We looked at albumin as a model of an anesthetic binding protein. We were able to show very nicely there was specific and nonspecific binding. You could displace it with different anesthetics and look at a range of concentrations. And so now we published a paper called Binding of Halothane to Serum Albumin up here in anesthesiology, and again down here with a different technique using tryptophan fluorescence quenching. Now we got the West Coast's attention. So Ted and Don Coblin, basically this was a letter to the editor, questioning the whole relevance, first of all, of using serum albumin as being a relevant target to study anesthetic mechanisms. But the premise of their argument really came down to this, and that KD values, in other words, affinity, for a particular target should match clinical EC50, the MAC equivalent, if those targets are important to producing anesthesia. And that there should be a preserved rank order of this KD and EC50 relationship for other anesthetics as well. So we thought a lot about that. This basically implies that there might be just a few important targets. And this especially indicates that there's maybe even only one or two important targets. And so this came down to an issue as to whether there was an important protein target, like the GABA receptor, for example, or could there be many? So we thought about this a lot and undertook a whole lot of experiments. This is Mary Ellen sitting back there, who actually conducted most of these. And we looked in whole brain. We took the brain and then looked at this is radioactive halothane, and showed that there are a lot of anesthetic binding proteins, and they're displaceable as you add cold anesthetic. We did 2D gels, looking at the number of the proteins that were there. We did theoretical maps of structures and how many cavities they have as a surrogate for how many proteins there might be that bind anesthetics. But the bottom line of all this work was this, and that is that there are many specific anesthetic binding proteins, perhaps as much as 10% of the proteome. And if you know, the proteome is about 300,000 proteins. Just for the time being, leave aside the interactome, which is much larger, but 10%. There was some evidence for binding selectivity, and those targets are distributed widely throughout the brain. There are a lot in mitochondria and regions of high synaptic density, which all makes sense, but there are a lot of different anesthetic binding proteins. So now we were emboldened to take this stand because we had gotten tired. And actually Mike Todd, who was the editor of anesthesiology at the time, thanked us for this because he was getting tired of hearing the phrase clinically relevant concentrations of anesthetics for in vitro experiments. And he didn't know what that meant. We didn't know what that meant. And so we thought about it a bit, and we put together this paper, which basically said, if you have one target here with a KD, let's say, 1 millimolar, which is 5 times MAC, obviously you're not going to have much of an effect at MAC. But if you have 10 targets, now you have a large effect. If you have 100 targets, you have a lot of effect. And look how this dose response steepened as you got an increasing number of targets. Instead of one target controlling everything, you have a lot of targets, each contributing a little. So we thought, based on this and based on our prior work, that in vitro sensitivity alone can establish the contribution of any given molecular target. Okay, so we published this. I can't believe we got it through, actually, because the response that we got was pretty dramatic. So, in fact, some of it I couldn't even reproduce here for polite conversation. It's the one from Nick Franks was just amazing. We had failed to cite him. Then this happened. So this was about a year or two later. Ted got together with a bunch of his colleagues, and look at this list of people. Ted, Alex Evers, Dennis Fisher, Nick Franks, Adrian Harris, Jim Dilger, Jim Sonner, Joan Kendig, a real cast of experts to look at this. And so our view at the time when we saw this was basically this. Come on, they're just the two of us, associate professors, And so we thought about this some more, and we looked at the paper more carefully, and it turns out they actually observed the same thing. They did the same kind of modeling, and they showed that if you increase the number of targets, you steepened and you shifted the curve to the left. But they had a completely opposite conclusion. And their conclusion was that in vitro sensitivity should not differ markedly. Of course, they didn't define markedly, but shouldn't differ markedly from clinical sensitivity. And one or two receptors mediate a specific anesthetic effect, such as amnesia and immobility and so forth. So we thought a lot more about that as well. How, again, this comes back to the issue of many targets or few targets. And so we decided to further our work in, before I get to that, Jim Sonner thought about, let me go back a slide. So, go back 2 slides. So this phenomenon is basically what mimics a Mach curve. Mach curves have these very steep relationships. It's called the hill slope. Very, very steep, 20 or so hill factors. That's unusual for drugs. That's unusual for almost any of the other drugs that we use as anesthesiologists. And so we thought maybe this had something to do with the number of targets, but there's other interpretations as well. And one of those interpretations, Jim Sonner published, and I think, Steve, you were editor at the time when this appeared. So this was really interesting. So basically, Jim, who is a direct mentee of Ted Eager, posited that there are sort of degenerate contributions that contribute to the anesthetic response, and that's what's being selected for to produce this lack of variability, these very steep dose response curves. And Steve, you sent it out to 4 reviewers, as ANA is wont to do, God knows why, but it went to 4 reviewers, and each reviewer had a different view of this. I think it was initially rejected. And but when you looked at the reviews, they were fascinating. They told a really broad story of what the different views of this phenomenon were. And so those reviews, it turns out, were published side by side with the paper to sort of like a mini symposium. In fact, I think this might have been the beginning of the mini symposium. Whoops. And these are the papers that appeared alongside of it. And this is a fascinating look at this subject of lack of variability to an anesthetic response, which is something that Ted Eager described many years before, but hadn't gotten into this level of detail and thinking about what's it due to. And so I highly encourage you. This was published in ANA 2008, not just because my paper's there, but because this is just a great discussion of the topic. But we continued to think about this, and we continued to think that we could contribute to an understanding of one target, few targets, many targets. And so this is where I'm going to talk a little bit about some of the recent results. These are unpublished results. But for example, in canonical anesthetic targets like the GABA receptor, we've made a lot of progress. A lot of this is due to Keith Miller, who's also here in the room, and others. And So for example, in the GABA receptor, this is John Cohen up here and Selwyn Jayakar. Using a compound that we developed, azpropofol, we're able to map out the propofol binding sites in the GABA receptor. This is work that Ted in his later years was really working towards using a variety of different methods. Nick Franks at the same time, using this compound, also pulled out some different sites, but we made a lot of progress in understanding where propofol sites are. But the really enigmatic anesthetic drugs are the volatile ones. They're the ones that we have much less of an understanding. So this is unpublished work. It hopefully is going to be published shortly. So Keith contributed dramatically to this to give us the alpha beta gamma and the alpha beta gamma receptors. This is a talented postdoc. This is the chemist that I've worked with for over 20 years, Bill Daly. This is a really talented undergrad who's now an MD PhD student at Northwestern. To bring back, there are a few of us from Northwestern in the crowd. Tom, myself. Anyway, so we have that commonality with Ted as well. And so basically, we developed a new compound, azsevoflurane. We already had az-isoflurane. We showed that they acted just like their parent compound on the GABA receptor in the how much they enhance it, and they're also suitable anesthetics, reversible, safe anesthetics, at least in the tadpole. And now we know where they bind. So using photolabeling, for the first time now we understand where volatile, not propofol, not etomidate, not barbiturates, but volatile anesthetics bind in an alpha beta gamma receptor, a typical synaptic GABA receptor. So these are the sites. They're interfacial like propofol. Some are intra subunit, but this just shows the range of targets. And what you should take from this slide is the complexity, is the number of sites and the complexity of those sites. This is something that was unanticipated, and it's something we're going to have to work out what each of them mean as we go forward. That was isoflurane. Here is sevoflurane. These are the binding sites for sevoflurane in the alpha beta gamma receptor, showing again they bind at these interfacial cavities. This is the kind of stuff that I think if Ted's looking down on us now, he would like. And the messages from this work: multiple largely interfacial sites for both volatile anesthetics. Some overlap with each other and some are distinct. So the different flavor that we have for sevoflurane versus isoflurane may be reflected in the sites that they bind in a single receptor. So that's a new way to think about this. Most of these are specific, i.e. displaceable, and the actions do not necessarily align. In other words, the actions of occupancy of one interfacial site might do the opposite to the actions at a different interfacial site. So sort of a self-antagonism with the same receptor. So this is another interesting feature. The other thing that we can get from photolabeling is identifying novel molecular targets. This is a particular interest of mine. I don't think everything is the GABA receptor. I've gone on record for that. And so we've identified binding sites and mechanisms in the voltage-gated calcium channels, voltage-gated potassium and sodium channels. This is a KB 1.2 shown here. Turns out there's probably a preserved canonical site within these channels. And we think we understand the mechanisms now as a result. Off-pathway targets. We all know that volatile anesthetics, as well as propofol, have side effects. Some of those side effects are important. And we think that we're now beginning to understand what some of those side effect targets are. This is just a couple examples. SIRT2 is a deacetylase that's vitally important in regulating the intracellular environment. LFA1 is an adhesion protein vital for leukocyte binding to endothelium. And we understand now how anesthetics affect both of those, and they affect both of those at clinical concentrations. This I just had to show because it's so cool. This is kinesin dragging a vesicle along a microtubule. Isn't that cool? Look at the way it walks. These are the motor domains down here. This is this tether, and these are these very specific attachment proteins that attach vesicles. Why am I showing you this? Because it turns out that it's very, very sensitive to anesthetics. Propofol especially, but also sevoflurane. And now we understand where the binding sites are and the mechanism by which it inhibits their motion. So what it does, it doesn't slow them down, it derails them. So what they do, instead of instead of just trekking along to their destination, they trek along at the same speed and then just fall off the track. And so we're trying to understand what the implication of that is for anesthetic mechanisms, for side effects, and so forth. Now, I'm going to end up with this. So, what is this? So this is a proof of principle experiment that I did with Bill DeGrotto. Bill was at Penn many years ago, but he is here now at UCSF. And if any of you are interested in really, really, really understanding protein chemistry, this is the guy to go talk to. He's totally amazing. Anyway, so we took this monomeric system, and we found that if you designed it in such a way that it oligomerized and formed a cavity when it oligomerized, then if you add an anesthetic to it, you promote that oligomerization, you promote that aggregation. And that's shown by analytical ultracentrifugation right here. So, so what? Well, there are an entire class of neurologic diseases based on protein oligomerization or protein aggregation, Alzheimer's, Parkinson's, and so forth. So it was a natural step to start looking at this. And here we published this paper, and then Mike Todd thought this was kind of cool, so he published this over the objections of some of the reviewers. And rapidly followed by some work from Sean Kong, and then we published this after that. And so this initiated a whole field of what are anesthetics doing to the trajectory of Alzheimer's disease? Now, you've noticed I haven't mentioned Ted for a few minutes, but Ted came back on this one. So he published this. He published this editorial in Annals of Neurology, pointing out the fact that, yeah, okay, in mice you can get this to happen, but every clinical study that's ever been published hasn't found this. And so he said at the end, perhaps old humans are more robust than young mice. These two authors hope so. This is Adrian and Ted. And I'll have to say at this point in time, I've been interested in this topic for a decade now, or more than a decade. I think he was right. I think that what we know now about the inhaled anesthetics or any anesthetic is that the impact, the contribution to a change in trajectory of Alzheimer's is minimal. And it's very, very difficult to demonstrate in people. So I'm just going to end with this. I was personally honored, and our institution was honored to have Ted come and deliver the 15th annual James E. Eckenhoff Memorial Lecture. That's my dad. Here's Ted. And at that lecture, he told us about the wondrous story of anesthesia, and it was fabulous, well received, and we just loved having him. So, and with this slide, I think we've all been carrying small stones for many years, and I think perhaps the generations of mentees that Ted has had will at some point reveal what's under the mountain. So thank you.